Hi guys. All right, we are starting in on starting in on chapter 6, and that is energy. This is a pretty short little chapter, but it is going to help us as we go on. So, and a lot of it again will be common sense, like some of the stuff we've already done. So anyway, so energy is needed by everything. Every living thing requires energy, and in some way, we then use that energy and use it to do things. In nature, different processes are driven by energy. The water cycle, the wind, earthquakes, volcanoes, all those are different forms of energy. And we use some of those forms of energy to use for ourselves. And I have that big long blank in there on this slide that says that energy is used by people for, and pretty much everything that you can think of goes in there. So any of our devices, our cars, our own bodies use energy, and so it is a big deal. And then that last thing, it holds matter together. I've told you before that if we could separate everything in the universe, everything that we know, if we separated it to two categories, one would be matter and the other would be energy. So when God created everything in the beginning, He created matter and energy, and we've been rearranging it ever since then. But essentially, it is energy that is holding everything that we know of together. Okay, so energy is not something that I can't hand you. I can't say here is energy. So it's very hard to define, but we do see what it does. We measure it, volts, amps, those kinds of things, a current of some sort. We can convert it into matter. We can use it to do work. We can convert it into other forms of energy. We know that it is a positive scalar unit, and the unit that we give to energy as far as physics goes is joules. But we define it most often as the ability to do work. And work is done if an object moves a distance because a force has been applied to it. The unit for work is joules, so it's just like energy in that case. And when a system does work on its surrounding, the system will lose energy. When a surroundings do work on a system, then the system gets energy. And so it's a very movable quantity. It is very easily converted. Comes in different forms, and so it is hard to really pinpoint what it is. All right, so now two big, I guess you would call categories of energy are potential and kinetic energy. And potential energy is defined as the energy of position or the energy of condition. And usually people will say that the potential energy of an object depends on the system or the object's position, like how high up it is off the ground, and a force that could move that system. The picture down there of the two guys, the hill, before that ball rolls down the hill, it has a lot of potential energy because of its height. It has the potential to then roll down the hill if that man applies a force and pushes it. So it's where it is and then what could happen to it. And the force could be any field force, so gravity, electrical or magnetic field forces, and some contact forces like that guy pushing. But they all rely on where the system is to begin with. And then kinetic energy is the energy of motion. So as that ball is rolling down the hill, it is showing kinetic energy. So anything that is moving has kinetic energy. All matter has moving parts and the atoms that make it up with the electrons. And so there is always energy, kinetic energy in something, and it depends on the matter's mass. And then if you're talking about the system as a whole, the speed at which that system is moving. So now, classifying energy, there are 9 types of energy, and some of them will go back to, we can talk about the potential energy or the kinetic energy, but they can all be converted into another form. They all have the capacity to do work, so cause a system to move. And as the forms are converted from one to the other, work can be performed, or the energy is put into a form that is a storage type energy. Okay, so first off, mechanical energy. So this is possessed by objects that are in motion or that have the potential to move. So the little picture that I have there, the water, kind of up above, kind of on the flat area, so right up here, that has potential energy. As it falls down over the cliff, as it becomes that waterfall, it is kinetic energy. And then it then is going to turn that wheel down at the bottom to become mechanical energy. And so wind and windmills are kind of a typical example of mechanical energy. This water wheel is a form of that. You riding a bike is mechanical energy. And so in its two forms, either the kinetic or the potential, there are formulas. Yikes, I know that means there's math. And we'll talk about these, and you guys will do some practice problems. But for kinetic energy, you have this formula, and it is 1/2 the mass of the object times the velocity squared. This should look really familiar math-wise to the distance formula that we used in chapter 5, and you'd work it the same way. You would square your velocity, you'd multiply it by the mass, and you divide it by 2. And that will give you the kinetic energy, and the units will be joules. Now, and this G is for gravitational. So potential energy, like we said, depends on height or the position, which generally means that gravity will be the force that moves it, that pulls it down. And so this is gravitational potential energy. And so the formula is work times height, and this is actually the formula that I want you to use, mass times gravitational acceleration times height. Because remember that work equals mass times gravity. And so that's where that formula comes from. And you multiply all of them together, you get your answer, and that is joules. Okay, so now thermal energy. This one is one that we are probably the most familiar with, even though we don't really think about it because it has the most to do with temperature, of course. And so this is related to the motion of molecules in the matter. So the more motion, the more thermal energy. And so a gas has the most motion of the 3 states of matter, and so it technically has the most thermal energy. As you warm things up, as you boil them, they go from a liquid to a gas. So that is kind of showing that change in motion. There is a point that theoretically that we believe that all motion will stop, and this is called absolute zero. This was a calculated number, and it's calculated by a man named Lord Kelvin. I can't think of his first name right now, but he said that at this moment all motion stops, and he calls this absolute zero. On a temperature scale, it's calculated again to be negative 273 degrees Celsius, or what he said was 0 Kelvin, named it after himself. We've never achieved absolute zero. The thought is that if you stop all motion, then it will kind of cause a chain reaction of stopping all motion, but we've come close. And so if you slow it all down enough, then you can stop this thermal energy. Heat is what we're more aware of, is the transfer of thermal energy. So thermal energy moving from an area of high energy to lower energy. When you cool something down, you lose thermal energy. When you heat something up, an object gains thermal energy. And so in our little picture up there, it's showing several different it's labeling several different things, but what I want you to realize is that heat is transferring or converting energy into motion as the water molecules in that pot start to boil. As far as we are concerned here on the Earth, the thermal energy that we get from the sun is our ultimate source of power. It circulates the air in our atmosphere, which causes wind. It runs the water cycle. It does lots of other things we'll actually talk about with some other forms of energy. All right, acoustic energy is our next one. This is energy that travels in waves through matter. So it has to be carried by a solid, a liquid, or a gas. And it's caused by mechanical vibrations, and that is mechanical energy, actual motion. Earthquakes are acoustic energy. Explosions, like the, kind of the, like when you see in a movie and there's an explosion, and even though the people aren't super close to the car, the building or whatever explodes, they get like blown backwards. That's acoustic energy. Bass speakers, and you guys have all kind of heard and felt that that energy. Human vocal cords, bats use a form of energy to determine where they are. Dog whistles. So that picture over there shows this dog is barking and he's producing sound waves. His vocal cords are making are causing waves that are carried through the air, and they go into your ear, and there they vibrate your eardrum. And so they are a wave that is carried through air. In this case, that's what sound is. So as you hear my voice as I'm speaking on this recording, it is causing sound waves to move through the air from the speaker. Those sound waves make your eardrum vibrate. Your brain translates that into words. Okay, electrical energy, this is the one we're probably think we use the most. And this is associated with charged particles flowing through a conductor. So from a power source, like where you plug it in essentially, through a wire to a lamp, or to your phone as you charge it, or whatever it is. We have been able to create batteries. We use generators. PV cells are photovoltaic or solar cells. And so we have different ways to store and then release this energy. Natural sources of energy, lightning is probably the one we think of probably right off the bat. Electric eels have a way to create their own energy. The electric currents that are in the Earth's magnetic fields, those two are very closely related. Your heart produces a slight electrical charge. That's why they can do like an EKG to measure your heartbeat and that kind of thing. And so that one to us is probably, it feels like the most relevant. Magnetic energy, I've got a picture of a compass up there. Certain substances that are magnetic are affected by the magnetic field. And so this energy comes from magnets, and it comes from the fields that are around them. And it has the ability, this field or these magnets have the ability to attract or repulse other objects and cause them to move. So on a compass, your compass is attracted to the North Pole, to magnetic north. And so that's why the little dial in the compass will swing and always point to north. And so you can use it to kind of tell direction. All right, radiant energy. The thing with radiant energy that I want you to understand is that it can move through a vacuum. It doesn't have to be carried by a substance like acoustic energy does. And this essentially is what we think of as light. But it can be any form of radiation, and it is the ultimate source of energy in our universe, and the sun is the big thing. There are other examples of this: radio waves, infrared waves, visible light, like I said, ultraviolet waves, which you're not seeing, gamma rays, X-rays. But as far as the ultimate source of energy goes in the universe, that comes from the sun, and it is a source of power, not only for like us being able to collect it, and solar panels and plants being able to use it and all that kind of stuff. But like I said before, it really runs our atmosphere and our cycles. Okay, chemical energy. So plants use photosynthesis and change that radiant energy that we just talked about into chemical energy, which is a form of a sugar. Any food that you eat essentially is chemical energy, and there's potential energy in there and it is stored in the chemical bonds of the compounds. So as you are, like carrying your lunch around in the mornings before you go to lunch, you're basically carrying around chemical energy that has been put into those foods by plants originally, and either eaten by animals or packaged differently by us, but you're carrying around chemical energy. And when you eat that chemical energy, your body releases it and converts it into other forms. Your muscles move it to use it to move. Your brain uses it for some like electrical energy to fire neurons and to help you think. There's some heat produced, so you keep your temperature steady. And so it is, for us, obviously extremely important. All right, nuclear energy. So of course I have a picture here of a little mushroom cloud. I could also have put a picture of like a nuclear power plant on there. This is a big source of energy that we're still trying to kind of figure out. It comes from the nucleus of an atom, and it is released either by splitting an atom, like we use in the nuclear bombs and like we use in nuclear power plants, or fusing two nuclei. And this is called fusion. It's a really powerful form of nuclear energy. We're still trying to work on it, but we have an awesome example because this is what is happening in the sun. And so the sun is constantly fusing two hydrogens together to form helium. And when that happens, it releases all forms of energy that we get from the sun. Radiant energy that we just talked about, light, heat, all these different things that keep our Earth going the way that it should. Okay, and then we have mass energy. Mass energy is the energy equivalent to matter itself. This is what Einstein theorized in his formula E equals mc squared, and that's the energy that you, sorry, typo there, you would obtain if you could convert all of an atom's mass into energy. So if we could take the energy in a very small object and multiply it by the speed of light, because that's how fast the electrons are moving within each and every atom, then we would get the energy out of that substance, out of that object. And so essentially we could take something, I believe your book uses a problem like you could take a banana and its mass times the speed of light and produce enough energy to run Bartlesville for like years. And so it is a theory that has been proven. It was actually part of what was used to help with nuclear bombs and those kinds of things. But it is the one that really unites energy and mass. Okay, so now energy conversion. So like I said, energy is constantly being transformed from one type to another. So from mechanical energy to electrical energy, or from radiant energy to chemical energy, those kinds of things. And so it's a constant. In the world, though, we say that energy transformations are never 100% efficient. Some energy is always lost, and we consider it unusable. That lost energy is actually what becomes heat. And so it's unusable in an actual system, although it does have a use. And this percentage is very often referred to as efficiency. And that's the comparison of the amount of usable energy compared to the amount of energy before the transformation. Most man-made transformations are less than 20% efficient. We lose lots of energy as heat. All right, and these energy conversions follow the first law of thermodynamics, which says that energy can never be created or destroyed, it only changes form. So the amount of energy that we have now is the amount of energy that God put in place in the beginning. We simply keep converting it back and forth between the different forms. Now, a pendulum, and that's kind of what this picture is supposed to be, is a good way to study motion as it's related to energy. And so in this pendulum, you have 5 different positions, And depending on what is happening, you see kind of a difference between the potential energy and the kinetic energy. And if we had measurements or numbers there, if you put added the two together, potential and kinetic, they would always equal the same number. You're never changing, losing, or adding energy. It is just, and so you are changing it, excuse me. You are just changing it from potential to kinetic. All right, so what this pendulum tells you, and I kind of already said this, is that all forms of energy are going to be equal to the amount of energy that the system started with. And so, so I just wanted you to think about when you have a car with a full tank of gas, what happens to the energy as you burn that gas? What does it get converted into? Okay, last thing, collisions and energy. So where does the energy go in these collisions? And there are three classes of collisions, elastic, partially elastic, and inelastic. Elastic collisions are actually theoretical. They don't happen in the real world because friction is here. Objects get deformed here. They don't go back to completely to their original shape. But inelastic, theoretically, when two objects collide and they rebound, the sum of their momentums and the sum of their kinetic energies are going to be the same before and after the collision. And so, so this is like saying if two people run at each other with those big exercise balls with a certain amount of energy, they hit and they would move right back to where they started because of the energy pushing them back. That doesn't happen if you've ever seen those videos, but that's the theory. Partially elastic you do see quite often in the world, and this is when one or even both objects in the collision are deformed in some way, and some of the kinetic energy is converted into heat. This happens all the time in car wrecks. This happens with the people in the big exercise balls. Someone will not bounce back as far as the other person. You'll always have some loss of energy. And then inelastic collisions, this is when the colliding objects basically stick together. And so sometimes you do have car wrecks where the cars themselves are so deformed that they get kind of stuck. And there's lots and lots of heat produced in those types of collisions. And the kinetic energy is greatly changed as all of that happens. Okay. Thanks, guys. We'll go over all of this, of course, in class together. So if you're using this as a review, just kind of go back through. If it's the first time you're hearing this, be sure and ask me questions if you don't understand it. Thanks.